one, converting is saying getting close to a, or going to a certain point. What types of functions converge?
With the asymptote. One with the asymptote. So like one of the y, one of the x.
I have a question. If we fail the chapter 10 test, but the rest of our tests are good,
I dropped to an S.
oh, what?
Failing test dropped you to an S. But anyway, what type, remember, what we talked about arithmetic sequences, geometric sequences, right?
Yes.
What caused one of them to converge?
Geometric.
Geometric in what sense? Or when, in what case?
With the fraction.
What do you mean with the fraction?
The one with, I don't know, that was so long time ago.
But we're still in the same chapter, we're still dealing with the same stuff. So, we did infinite series, so n equals 0 to infinity of, let's say, 5 times 1/3 the n.
That's what I meant, with the fraction. Was that wrong?
Okay? So what do you mean by with the fraction?
Because the fraction, the portion adds, then it equals 1/3, 1/3.
Okay, so numbers that have a common ratio where the ratio is between -1 and 1. And what does this converge to?
That conversion.
What's the rule? 1 over, or 1 minus r, remember that? Or a1 over, does that look familiar?
Yeah.
Okay, so this is going to be our basis for what we're going to be doing today.
Isn't that conversion to 6? Hold on, isn't that
I
conversion to
think this was 10.3?
Wait, that converts to 10.3?
No, I think this, if I remember correctly, it's from 10.3. We either talked about infinite geometric sequences.
What does that converge to? 6?
Let's see, if you plug in 0, so 5 over 1 minus 1/3. So 5 over 2/3, 15 over 2, 7.5. So, but this is our basis for what we're going to be doing. That's just review section. What we're going to be doing is, our goal is saying, we want to have a function and be able to write it as an infinite series. So for example, let's see, this one. G of x equals 1 over 3 minus x. And we want to write this as a sum of an infinite series. However, it won't converge everywhere. We're going to say, and what range does it converge? So first thing we want to do, we're going to say f of x, or sorry, g of x equals f of u, where f of u is equal to 1 over 1 minus x. Or 1 minus u, sorry, no. Does this look familiar? Look a bit like, oops, this. Okay.
Like
So,
what?
like our, this is our basis. So, we want to do this and say 1 over 3 minus x is equal to 1 over 1 minus u. And now we're going to be solving this for u. We're going to solve this equation for u. So we can just flip each side, so 3 minus x equals 1 minus u. So 2 minus x equals negative u, so u equals x minus 2. X is our variable in g of x here. Now, what this means is f of x, or g of x is equal to f of x minus 2. So if I plug f minus 2 into here, or if I plug x minus 2 into f, I would get back this.
Where would you put it?
So if I did f of, what was it, x minus 2? Yeah.
Wait, why is it saying 2?
That's what I solved for right here. I said u equals x minus 2. If I plug this in, what do I get?
You get 1 over 3 minus x.
1 minus x minus 2, right? Which becomes 3 minus x. Which was what I started with g of x. So basically we're saying, what value would I have to plug into x? 1 over 1 minus q is this, in order to get this.
Is that to be always value?
Yes. Because the goal is what we want to know, when does this converge? And this converges, what has to be true about u for this to converge?
That's the R.
That's our r. And what has to be true about r?
I forgot what R is.
It has to be between 1 and what?
0 and infinity.
Negative 1 and 1. Yes. Sorry, that's you. So, well, we're not done yet. So, now, the next thing we're going to be doing, we can say, our goal is to say g of x, or the circle is equal to sum n equals 0 to infinity of something.
What happens there?
Up where?
To the right.
Oh, here, I was just showing that if I plug this part right here into u, I get back g of x.
So what's the answer?
Okay, we're getting to that.
No,
No, we haven't. I'm showing you, this is our goal. Is we have to write g of x as an infinite sum. So,
The infinity above the six thing, is that constant or linear?
it's infinity.
Oh.
So, I'm going to rewrite this as f of x minus 2 is equal to the sum n equals 1, or not 1, 0 to infinity of x minus 2 to the n. And I'm going to say our rule was x minus 2 has to be less than 1. Okay, now think about what this is saying. Does this look familiar? Okay, this is a geometric sequence where it's u or a to the n, or a to n minus 1. And it converges when what's true? Well, when whatever we're raising to a power, the absolute value of it is between negative 1 and 1. Okay, so everybody with me on that. So does this make sense? Remember this is a 0. Now, we have to solve for what range of value. So how do I solve this equation? Or inequality, I should say.
Isn't it negative infinity to
No. How do you solve an inequality of this sort?
You do, so, oh, I know, you do x minus 2 or
X minus 2
3 less
is
than,
less than 1.
or,
Is it going to be and or?
that or. Why?
Anytime it's less than, it's always and.
Why?
Okay, let's
No, but you don't write it like that. You don't write it like that.
why is it?
You write it as a negative 1 and be less.
It doesn't matter.
That's the rule.
So plus
Breaking
2.
the rule, math.
So x is less than 3. And say add 2. X is greater than 1. So would it make sense to say less than 3 or greater than 1? What numbers are less than 3 or greater than 1? 2. Is 5 less than 3 or greater than 1? Yes, it's because it's greater than 1.
It's not less than 3.
It doesn't, I said or. If I said an or, if this is an or instead of an and, then if any number you chose, 1 million is greater than 1, therefore it would work. So or does not help us in this. We need an and.
2.
So 2 works is for an and.
2.1.
That works for and,
2.0.
but not and for or. But our goal is we want a restriction, so we know this is going to be an and. Because if we had an or, then this would be no restriction at all. Right? Okay. So our answer, we could say g of x is equal to the sum as n equals 1 to infinity of x minus 2 to the n, and x is between 1 and 3. So let's look at the graph of this.
Why does it have to be? How did you get that?
Get what?
How did you do that?
Where did one come from?
Where's 1 here?
The other one.
Oh, sorry, 0.
Yeah.
I keep writing, I'm sorry, I keep writing 1 because we were doing that earlier, we almost always did 1
So
and
you
0.
just, we have a restriction that the one has to be less than
The x is between 1 and 3.
y. What is it?
Okay, that came from this right here.
Why does that have to be less than one?
Okay, because in order to converge, what has to be true about our ratio, our common ratio? The absolute value of our common ratio must be less than 1.
So, but it can be less than 0 too, right?
Yeah, that's between, well, between negative 1
So
and 1.
therefore, it always,
Oh.
So this converges between 1 and 3. In other words, if I added this up, I would get the same number for this as I got for, remember, what was g of x originally? So let's graph these.
Wait, if it's supposed to be bigger than negative 1 and smaller than 1, why didn't you specify that on the right?
Right here,
No, in the, up,
up here,
no, on the right.
right
Down? No.
here?
No, in the box.
in the box.
Yeah.
I'm not sure I follow.
You only put it has to be less than 1, they both have to be.
But that's why I put the absolute value. Absolute value right here. And therefore, when you solve an absolute value, you separate it into 2 problems and solve each one. You see it now? Okay. Okay. So, how would you write this out if we were doing the first 3 or 4 terms of this? What would the first term be? 1 plus, what's the second term?
X minus 2.
So the first power plus
X squared plus,
x minus 2. Let's just write it out in this form.
oh,
Just make it a bit easier.
X minus 2 in the third.
Okay,
Four
so,
terms. Is that five?
yeah, that's 5 terms. Let's just do 5 terms. And we want to compare this, the addition of these to just 1 over 3 minus x.
Does it have to equal 1?
Well, we want to compare it.
What does that have to do with 1?
These should, if we did an infinite sum, these should be equal between 1 and 3. So let's see, I'm going to graph on here.
have you seen me blue calculator story?
So y equals, let's see, 1 over 3 minus x, and the other one is 1 plus, say, x minus 2 plus x minus 2 squared plus the third plus x minus 2 to the fourth. Okay, and let's look at the graph.
Do we have to do it that way? Or is there any way?
The first problem.
Okay, so if you notice, from about here to here, these are basically the same. That was our goal, is looking from at what point are these graphs the same. So it's about from there to there. So let's see, what is my window set up to?
What was our goal?
Our goal is to be able to write a equation. Now the first one was this right here, right?
Yeah.
Our goal is writing an equation, an infinite sum, that would emulate this behavior of this graph. And so we found we found an equation that will do it from point 2 to 3. Or from 1 to 3, sorry, not 2 to 3, 1 to 3. That's what we did here is,
What's the question?
okay, the question is, write a, or find a power series representation and an interval in which it is convergent, it converges.
Oh.
So this is the power series, right here, and it converges from 1 to 3.
How was the right hand in calculating?
This,
Wait, so what?
so the answer is this right here,
So that's the power series, and then,
and then the where it converges is from here to here.
okay. But then, how is that different from what the answer is?
This is what the answer is.
Oh.
This is the answer saying g of x is equal to this power series,
So the other part is testing.
this right here.
Yeah.
Yeah, this is showing what we're going to graph. We're just testing this graph and saying, we plug this into the graph and they go, well, you know, they do match from that point to that point.
So is the equation above the green box?
This right here. This is what we started with. So we're saying we can say 1 over 3 minus x is equal to g of x. So 1 over 3 minus x is equal to this from 1 to 3.
And you got that using the f of u?
Yeah, using this whole process. Yeah.
Is the one that you got for the initial, like the absolute value
Right here.
is that just the cost, the numerator of?
No, that was taking this part right here. Because our rule for this
Oh,
converge,
yeah, just to the zero, or, right, to the zero in, or,
well, this part here,
yeah.
it's just saying that whatever we have in here, in order for it to converge, that value must be less than that.
Oh, yeah.
That's how we got this x minus 2. Okay, so let's do another one of these. This is the more complicated part of this. What's your question?
How do you write x?
Okay. You write x minus 2 plus x button minus 2.
No, but like, if you do the and 2 with an x.
Are you talking about the infinite sum?
Yeah.
I'm not sure, it's a bit complicated. Oh, I'd have to look at it
How do
further.
we put that in our calculator?
Well, no.
Do we need to?
No. Because usually it's going to say just graph the first 5 terms, 6 terms, or something like that. So here we did an estimate of the first 4 terms. Now we could, of course, add a couple more terms in, be even closer and closer to it. But we just look at the graph here, we can say, yeah, they do look pretty close from there. So let's say, let's even zoom in a little bit, and maybe 0. Remember, that's the original one, and that is my power series. So right now it's not converging at 1, it's converging right about there. But we could add a couple more terms in there, and this is going to move back until we get to that point, and go on. Keep going. Mhm. We can get very close to it, infinitely close. So as everybody understand what our goal is when we're doing it. Yes.
Do you have to graph it on one?
Yes.
Do you think that's part of the test?
This is the hardest part. Yeah.
Oh.
So g of x equals 1 over 2 minus, or 1 over 1 minus 2x. So again, we're doing the same thing. We want to write a power series representation of this and find where this converges.
What is f equal? That's the only thing.
Yes. Remember, the goal of this, remember the reason it's shaped like that is what? This is what an infinite geometric sequence looks like. Remember the formula?
Oh, I thought you were the graph.
No. Let's see, where was that one? Remember our a1 over 1 minus r? So that's what as a view is based on, is this, that we can sum something up and we're going to get it.
Do we have another one?
We have what?
Do we have another one?
For infinite sum? I think there was 2 in the book, maybe, but yeah, they're equivalent. So what do we do first? Yeah, that's an equal to 0. So 1 over 1 minus 2x equals 1 over 1 minus q.
So just automatically do that.
Yes.
Okay. So we don't have to do the first part that you did
No.
for a long time.
This is basically, I think it's before I just said g of x equals f of u. And that's what this is contained. So then what do we do?
1 minus 2x equals
That's it.
1 minus 2x.
So 1 minus 2x equals 1 minus u. Subtract 1. We get negative 2x equals negative u. Therefore, u equals 2x. Okay. So everybody with me with that? Okay, so the next thing we're going to do, say g of x is equal to f of 2x. Okay, I was just saying that, notice if I plug in 2x here, it's going to be exactly the same. So, and then we can say this is equal to the sum as n equals 0 to infinity of what? 2x to the n. And what is the restriction? Yeah, because remember, that's the only way that this converges, is when they're common ratio. Okay, so now we can say g of x is equal to sum n equals 0 to infinity of 2x to the n, and then how would we solve that? We can say 2x is less than is less than 1. Is it can be and or. And 2x is greater than negative 1.
What's the circumstance really before?
For any of these, this section, it's because we have a less. Less than is always in. If it was a greater than, it would be an or. Okay, so our restriction is that x is between 1/2 and negative 1/2.
I have a question.
Yeah.
G of x is equal to f of u, right? And
Would we, how does that relate to this on the bottom left?
This,
Or, yeah, that whole equation,
how does this relate to it?
yeah.
Okay, so this is finding out what our restriction is.
Oh,
Remember, we have to have a restriction because this is not true everywhere. It's only true in this range, that g of x is equal to this.
so would that not be the infinite value?
Well,
Would
if
that
we,
have a restriction?
well, we can, but n is infinite.
Oh.
So we can go from 0 to infinity. 0, we can plug 2x to the 0, 2x to the 1.
Other
or add-
restrictions beside x?
Yeah, what values of x you can plug in. N is not restricted, n is an infinite number.
How do you graph it?
How do you graph it? So we were doing is just doing a partial graph. And I was just saying like 2x to the 0 plus 2x to the 1 plus 2x to the 2 plus, and notice in the book it's going to say graph like a fish partial sum or something like that, which means you do the first 5 terms.
do I have to graph the first one? Or no?
Yeah. So some of them are going to say graph a certain number of times.
Can you graph it?
No, I did graph around last one.
Not with the graph calculator.
Okay. Now we plug in 0. What do you get? Plug in 0. Plug in 0 for all of it. Plug in 1. Plug in 2.
Oh,
In all the x's.
oh.
Oh,
Oh, like an x, y.
Yeah.
they're all 0.
If you plug in 0, yes.
So this will be on the non-calculator part?
I'm not sure I'm not sure if this test will have a non-calculator section.
Oh.
If it will, it most likely it'll if we do, it'll probably be primarily about can you do a sigma notation? Can you do these formulas, use the formula for sigma?
Did we just learn a sigma notation in this chapter?
Well, you should have learned it algebra too, but we talked about it this chapter. Now, there's a few other formulas. So that was, no, this is our power series. Yes. Exponential series.
Oh, there's the power series, cosine.
This is Jordan.
Yes. So, what is,
When I'm close,
you know what E is?
E is 2.2 something.
Okay, but E is a constant, right? 2.7 or 2.271828, something like that. But our formula, we can write the formula for e to the x. I think we already talked about this a little bit this year. N equals 0. We didn't talk about this, but it's x to the n over n factorial. So I think we said, expanded this out and just said it's continuing on infinitely. But this is what the definition of what e to the x is.
Which
With
would the
no
numerator be bigger?
Okay? What do you think? Oh, remember, this
That's
is,
what x is.
yeah, so, remember, this is not a, this does converge. So does that mean it's infinite or not?
Well,
Let's think about this. If we did x equals, I don't know, 5, e to the 5th, some of what you're going to ask you to do is estimate values of e. So it's equal to the sum of n equals 0 to infinity of 5 to the n over n factorial. Okay, so what does n start at? 0. What? 5 to the 0.
1,
What's 0 factorial?
0,
1.
1. So you get 1 plus, plug in 1. 5 over
Hold on.
1 plus, plug in 2. Plus, plug in 3.
1, 25,
Plus, 6 25 over 24 plus. Which one is growing faster? Right now, it is.
So
But think about it. This is, on the top, we're multiplying by 5 each time, right? What are we multiplying by next on this one? Well, times 5. And then times 5 on top, and then times 6 on the bottom. Times 5 times 7. So eventually, the bottom is going to be much bigger.
yeah.
Then that's why this is converging, because if we kept adding these up to infinity, it's going to come to a set value, right?
So what it starts doing is go down.
Well, what it's doing is going to look, if you were graphing it, it would look like this. Because now, once we get further and further along, we're adding basically 0. So we're not. So here we're going up a lot. Like we're going up by 5. Now we're going up by 12.5. They're going up by like say 120 divided by 6, 20. Then going up by but no. Once we start getting over here, we start going up by a little smaller and smaller amount. So actually, it might look more. Maybe not. It'll be steepest in the middle here, and then a little bit flatter over here. So maybe something more like that. But this, eventually, is how we figure out the estimate for e to some power. And it'll say maybe find the 5th partial sum or find the 8th partial sum to get the estimate.
Can you graph y equals e to the x?
Yep.
What does it look like?
What does any power to the x, or any number to the x look like? It is exponential.
Good, but can we graph? So you say that's y e to the 6th, right?
This is approximately e to the 5th.
The graph.
It's the approximate what you get if you plug in 5 to e, or to x here. This is a constant, not a graph. If you're graphing e to the 5th, it's a line like that. It's a constant. So exponential series, basically what it's going to use is use this to estimate approximate values of it, of e.
Values or approximate?
Approximate value. I don't think you're doing any graph like this. With this.
So would the approximate value of that be
Well,
the biggest value there?
But it depends on how many terms it asks you to do. So if I did 1, 2, 3, 4, let's just do 5 terms. Add all 5 of these together. What do you get? And then, Victoria, do e to the 6th. What do you get for e to the 6th? Okay, so you got 148.4131591.
195.
Okay, 195.58, is that what?
65.375.
So that's,
Yeah.
okay.
Yeah.
So 65 point whatever. So in this case, it's not a very good estimate. Now if we went to another few terms, no, this is going to be a bit bigger. This is going to be almost the same as this one, and then it's going to be a little bit smaller, and so on. So if we kept adding these up, we're eventually going to get a good estimate. Now, power series. We talked about that. Now we're going to talk about power series representation of trig. So, cosine of x is equal to the sum n equals 0 to infinity of -1 to the n x to the 2n over 2n factorial.
Huh?
So you remember this.
I don't.
Okay, I was about to say, you remember this.
Say 2n.
This is 2n, this is 2n here. The sine is equal to 0 to infinity of -1 x to the 2n plus 1, sorry, to the n over 2n plus 1 factorial. So, if you wanted to calculate sine manually, however, you throughout your whole lifetime, you've had a calculator, or calculators existed, you can easily figure out the sine. Back, let's see, when did calculators start being to do sine? think it was probably the 60s or 70s. Before that, if you wanted to do the sign of some number that was not like on a unit circle, you had to do this.
Let's try sign of 9, how do you do it?
Okay, sign of 90 is too easy.
No, sign of 45.
How about sign of pi 8? Okay, so to do this, we're going to have first -1 to the 0 times pi 8, plug in 0 to the 1 over 1 factorial. Okay,
You add,
so first plug in 0 to all of the ends, and x is pi 8.
X is,
Remember x is pi 8 right there?
yeah.
but then how do people
Plus.
First you get 1 to the first pound.
Okay, -1 to the first, where?
Right there.
Like here, pi 8 to the first? Okay, 2 times 0 plus 1.
Oh. How did people calculate this without a calculator?
Okay? Well, you,
It's not without a calculation.
without being able to do time by kind of calculator. But you can also, if pi, we know pi is approximately 3.14159,
Is it?
and, yeah, and we can divide by 8.
How do you do that?
Because we memorize it.
This one.
But we can, this is something you easily do by hand.
Can we just do square root of 2 over 2?
-1 to the first, pi 8 to the third over 3 factorial. So no, doing it by hand would be very challenging. That's why back early 1900s there's a job called a calculator. This is what you were doing. This was your job, and it's primarily working on, you want to fire a shell at a certain angle. How do you calculate that?
Of course.
How did I get 3? Here? 2 times 1? Plus 1.
So what's the answer of sin times 8, according to that?
Then we have -1, with the next one to be -1 to the second,
Times to the 8.
pi over 8 to the fifth over 5 factorial.
There's a pattern. Look at
Yes,
the
there is.
pattern.
And we can keep doing this, and we can get closer and closer and closer, however close we want.
Would it be 135, 9?
Yeah.
11,
But this, your calculus homework then actually gives the estimate to the third or whatever.
So this is becomes a third.
Yeah, this is a third. And you keep going. We've got a couple more things we need to do here. 2 more things, I said. This is just an interesting fact. Euler's formula.
Do you know this?
Yeah. You should memorize it.
Actually?
Mainly because it's really cool.
Oh, I'm sure it is. Do we have to know more?
So, Euler's formula, or Euler, some people pronounce it. But the most interesting thing is this statement: e to the I pi minus 1 equals 0. That's what I get if I plug in pi into this equation. I theta cosine theta plus I sine theta. I times this, where? No, this is just I theta.
How is that 0?
That's an interesting fact, though. E to the I pi minus 1 equals 0. That you can take several of the constants, e and pi, and the imaginary number I, combine them, you get a really simple thing. Minus 1, you get 0.
So where do you get?
What?
So
So
pi is 1.
Yeah. But it's an interesting characteristic. And I think it's one of the more amazing things that you can relate E, I, and pi in such a simple way.
How is
Can you prove it?
Can I? Probably not. I'd have to start with this.
Yeah, but cosine of pi.
Cosine pi is 1.
Oh, 1?
Or -1, sorry. So it should be plus 1, not minus 1. -1.
Oh.
Yeah.
Negative 1.
Is it add 1? Sine of
0.
Sine of pi is 0. 0 times I is
Oh,
0.
that's why.
So it should be a plus 1. Yeah, I was thinking minus 1 didn't sound right.
Oh, that's why.
What's the other one? Did you actually
Oh.
memorize that?
No. But you should memorize at least this.
So EI squared is the equivalent to I squared.
What?
EI
EI pi squared.
No. EI pi is equal to I squared.
E the I pi equals the I squared. Yep. So the last thing, exponential form
There's a better way to do this, right?
of imaginary.
It's got.
So we did the trig form of imaginary numbers, now we're talking about the exponential form. A plus bi is equal to r e to the I theta. Where r is equal to the square root of, what do you think?
A squared plus B squared.
A squared plus b squared. Looks familiar, right? And theta is equal to
You're A.
where a is greater than 0, or does this part look familiar?
Yeah.
So this should look like exactly like what we did before.
Kind of
When did we do this? Like, what was it for?
This was when you're writing the trig form of when you're dealing 4 coordinates
So was it A?
and the trig form. What?
Was it just the 8 or 9?
I don't remember. But this is the last thing.
Let's just the 9.
So there's going to be some of the questions to ask you to rewrite this an imaginary number in exponential form. So if we had, say, 3 plus 4i, what is r going to be?
R is gonna be 5.
So this is equal to 5 e to the I and then here at theta.
So that's 4 over 3.
Inverse tangent of 4 thirds.
So will we be given the left side and we'll have to find the right side?
Like, yeah, like we give you this part right here.
53.13.
So can you give me radians?
You're picky. What is it, tangent of 4 thirds?
Inverse tangent 4 thirds.
0.927.
27i.
Why do you like radians? Can I do it in degrees?
No.
Degrees better?
Yep.
Why can't I do what I want?
Because it's not standard process.